Let's try to understand a simple concept in probability. That is, say you have a sample space. Okay, see, when you have a sample space, can we partition that sample space into multiple parts? In the sense, let's say you have this to be the sample space, okay, and we are trying to divide this into multiple parts. Say one part is like this, one more is like this, one more is like this, here, okay. So we can divide this into n number of parts, correct? N number. This is the first, second, third, fourth, so on and so forth till n number of parts. So every event in the sample space, because sample space is what? Set of events, correct? This is a set of events. Now this set of events, we are splitting them into multiple parts. This is what we call as partitioning of the sample space. Fine. Now here E1, E2, E3, so on till En. There are n number of events, correct? Now, if I take union of all of them, E1 union, E2 union, E3 till En, this is going to give us the total sample space S. Because one sample space has been split into multiple parts, correct? Also, suppose if you take intersection E1 intersection E2, this is going to give us null set. Because E1 and E2 has nothing in common with each other. They are called as disjoint sets, right? So these two events are disjoint event, correct? So a very important point here is, if you're splitting the sample space into multiple parts, what we call as the partitions, different partitions, those partitions, if you take the union of those partitions, that is going to give you the total sample space. And if you take the intersection, that is going to give you null set. So in general, we can say that EI intersection EJ is equal to null set provided I is not equal to J. Makes sense, correct? Now, the third, you can say the result of whenever we do the partition, which is obviously quite simple to understand, is that probability of any event we are looking at within that particular sample space is greater than 0. That means it's a non-zero probability. That means an event which will happen. However small the chances are, or however big the chances are, it will happen. So we can say that P of EI is greater than 0, where I belongs to whatever the set of numbers we have. So N, because generally we start with the first element, correct? 1, 2, 3, 4. We don't start from E0, E1, E2, right? Now, to understand the next concept, what we are going to do, these are more like prerequisites. Along with that, we also need to understand the multiplication theorem, whatever we have done previously. Okay. So, based on all these concepts and especially these three parts, whatever we have discussed, we are going to understand the next concept in probability, which is the total probability. All right. Let's try to understand what is total probability and how we are going to do the proof of the total probability. See, total probability talks about the probability of some event happening in the particular sample space, where the sample space has been divided into multiple partitions. All right. Let's say we can consider that A, capital A is some event, in sample space S. Okay. And this sample space, we are partitioning it into n number of events. That means S is nothing but E1 union E2 union E3 till En. So sample space S has been divided into multiple partitions, multiple parts. And event A is happening in that sample space S. Fair enough? So what we can do graphically, we can represent it, of course. But the mathematical proof of this total probability, like what the statement tells you, probability of that event A happening within the sample space is nothing but P of A is equal to, because happening, correct? So P of E1 plus P of A given E1 plus P of A given E2, so on and so forth, plus P of A given En. This is called as the total probability, or in short, if you have to write, we write it as sigma. P of A is equal to sigma P of Ei into P of A given Ei, where I is equal to 1 to n. So this is what we need to prove, or this is what we call as the total probability, because the probability of that event happening in that entire sample space, and also it depends on each and every event which is going to happen. Understood? And we have to prove this one now. It's a very simple proof and very logical proof if you actually think about it. Okay, let's do the proof of this total probability. See what you have. Assume that this is the sample space. Okay, this is S. And this S has been divided into multiple events. Correct? E1, E2, E3, E4, E5, like this, so on and so forth till En. Right? Say this is E1 and this is 2, 3, 4, 5 till N. Now, what we are doing is, you have an event A which is happening here, something like this. So, part of that A is happening in each and every event, because it's like this. Instead of taking one big bite from the burger, you're taking small pieces, and then you're not integrating, more like you're adding them all together. That's exactly what is total probability. One big event A is happening, and you're splitting that one big event into n number of small events, which is E1, E2, E3 till En. Fair enough? Now, that entire thing is the n number of events. And in each and every event, that E1, E2, E3, a piece of that event A is there. Okay, let me repeat. So you have one big event A, okay, and that one big event A has pieces, parts of it in all the small events E1, E2, E3, like that. For example, if you look at here itself, see, a part of this is there in E3 here, a part of this is there in E4, part of this is there in E2, part of this is En, isn't it? So, what is the probability that this event A is happening, given that E2 is happening, E3, E4, E5 till En? Understood? This is what we call as total probability. Now, let's do the proof. Very simple proof. Okay, we start with the sample space. So, S is equal to E1 union E2 union E3, so on and so forth till En. Correct? Now we know that event A is happening in that sample space S. Correct? So A intersection S is going to give us A itself. Makes sense? So we can say that A is equal to, now A intersection S, correct? That's nothing but A intersection E1 union E2 union E3 till En. Right? So now if you apply the distributive property, you're going to get A intersection E1 union A intersection E2 union A intersection E3 till union A intersection En. Makes sense? Very simple. Now remember, E1, E2, E3, all of them are disjoint sets, correct? See, if they are disjoint sets, then P of A intersection E1, A intersection E2, whatever we have, we might as well take, when you take the probability, instead of the union, we can take plus, because they are disjoint sets, correct? That means P of A is nothing but P of A intersection E1 union A intersection E2, so on and so forth, union A intersection En. Correct? Since all of these are disjoint sets, we might as well write P of A is equal to P of A intersection E1 plus P of A intersection E2 plus so on and so forth till A intersection En. Make sense? Since all of them are plus 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 plus, now we'll use the multiplication theorem. Okay, so the multiplication theorem, what did we discuss in that? P of A intersection B is P of A into P of A given B, correct? Or P of B into P of B given A, correct? So we'll make use of that here. That means this is going to be P of A is equal to P of A is equal to, the first one is going to be, see, P of E1 into P of A given E1, correct? A given E1 plus P of E2 into P of A given E2. See, like this, what do we get? Till dot 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 P of En into P of A given En. Isn't it what we are trying to prove? Because this is the total probability. That is P of E1 into P of A given E1. P of E2 to P of A given E2, like this, so on and so forth till here. See, this is the final result. That is the total probability of that event. Clear? So this is the total probability. What we have is P of A, that is probability of that event happening. This will be P of E1 into P of A given E1. That is event into the probability of A given E1 plus P of E2 into P of A given E2. Like this till the nth term. Or in general, we can write P of A is equal to sigma P of EI into P of A given EI, where I is equal to 1 to n. So this is basically what is total probability. Fair enough? So now let's try to prove that this is the case.